Hello, this video deals with an existence and uniqueness theorem related to first order initial value problems, or IVPs. So I'm going to go over 3 examples in this video related to this topic, right? To determine a region for which a unique solution to a particular IVP would exist. Right. So for all 3 examples, I have the following instructions. I'm asked to determine a region of the xy plane for which the given differential equation would have a unique solution whose graph passes through a point, say x0, y0. These are just representing numbers here, a point on the plane in that region. All right, so again, determine a region of the xy plane for which the given differential equation would have a unique solution, right, only one, whose graph passes through a point in that region. Alright, so the first equation I'm looking at is, dy dx, the first derivative of y with respect to x, or y prime, equals y to the 2/3 power. Alright, so in order to talk about the existence of a unique solution, in order to determine it for, we're only talking about for first order initial value problems here that look like this, where you have dy dx equals some function of the independent and dependent variable called f of xy with the initial condition y of x0 equals y0, which I've written over here. Just satisfies some initial condition. So in this particular example, this is already in this form where y prime is alone, right? Dy dx is alone. So this here, this expression on the right side of the equation, this is the f of xy that's being talked about here. And then let me state the theorem for you. And I'll actually pull it up from a website here. This is the theorem about the existence of a unique, over what kind of a region will a unique solution exist for a first order initial value problem. So here it is here. So given that the way that looked, right, that first order IVP looked, so suppose R is a rectangular region in the xy plane, right? So the x, a rectangular region, so the x coordinates range from, say, A to B, the y coordinates range from C to D, right, creating some rectangular region. And that contains the point that's mentioned in the initial condition, right? Right, it contains the point x0, y0 in its interior. If f of xy and the partial derivative of f with respect to y, hopefully you remember, Calc 3 stuff, right, partial derivatives, if they're both continuous on R, then there exists some interval, say I sub 0 over the values of x, some interval centered at x sub 0, contained in the interval for that rectangular region, the x interval for the rectangular region, and a unique function y defined on this interval that is a solution of the initial value problem. Now they say 2 here. What I drew on my paper was this initial value problem 2 that they're talking about. All right, this here. That's initial value problem form 2 that's being talked about in that theorem. Okay, so all we need to determine is where is f, all right, this y to the 2/3, and the partial of f with respect to y, where are those continuous in the xy plane? And it's in those regions where a unique solution will exist, that go through whatever point is mentioned by the initial condition. Again, we're not really focusing on any particular point. So the big question is then, on what regions are both f of xy and the partial derivative of f with respect to y continuous. Right. Okay. So that's the big question here. All right, so for this particular example then, f of xy is just y to the 2/3 power. This is continuous everywhere. All right, this is continuous over the entire xy plane. It's defined over the entire plane, same also, right? On entire xy plane. So again, there's no place where there's no values of x or y that make this expression undefined, right? Yeah. So now let's look at the partial. All right. Now the partial of f with respect to y. Remember, this means treat y as the variable in question, the variable that you're differentiating with respect to, and any variable that's not y, you treat as a constant. So if there were an x in here, you'd treat it as a constant, but there's no x's, so I just do this like normal. So this would be 2/3 times y to the -1/3. Now you could also write this as 2/3 times y to the 1/3. You could also write this, if you like your radicals, this is 2/3 times, the cube root of y. Now this should be, this is defined everywhere as long as y is not 0. So this would be continuous everywhere except when y equals 0. All right, so let's look. So putting these together, this is what we're concerned with here, right? Both of these have to be continuous. So let's look at the xy plane. I'm gonna make a rough sketch here. So again, the typical xy plane drawing, x-axis, y-axis. So I'll mark off y equals 0. All right. So I'll do it with like a dashed line here. All right, there's y equals 0. That's just the x-axis. So any region that I'm talking about, when I'm asked about, when they say determine a region of the xy plane for which this, initial value problem would have a unique solution, whatever region I decide to use, it can't contain this line. Can't contain any piece of this line y equals 0. So one valid region would be the upper plane. Say the point x0, y0 that was being discussed, that was in the initial condition, say that was in the upper plane. Well, then the region I use could be up here. Again, as long as it doesn't contain any part of the line y equals 0. So here's R, that rectangular region that is being talked about. All right, so a region that would satisfy this, that would guarantee a unique solution to the initial value problem, would be the upper half plane. Say the upper half of the xy plane. So anywhere where y is greater than 0. Okay, there's a totally valid answer. Right? Again, the answers can vary. I mean, as long as you don't contain any piece of this line, you'd be good. So another totally valid region then would be, well, what if x0, y0 were down here, right? What if the point in the initial condition were down here? Well, then I could take just the lower right corner, where x is greater than 0 and y is less than 0. Or I could take the whole lower half plane. Right? Again, as long as no piece of the line y equals 0 is involved, So another region that would be valid, again, as long as the point from the condition, as long as the point from the initial condition is in that region. So another possible region would be the lower half plane. Right, anywhere where y is less than 0. But again, another possible region could just be simply, if you know where the point is, could just be a simple rectangle around that region, as long as y equals 0. Any piece of y equals 0 is not in it. So there's another valid region, if this was the point in question. Right. Some rectangular region around it. But we're trying to make them as large as possible, though. Right, just like with our intervals of definition for solutions of differential equations, right? We're trying to make these regions as large as possible. Right. Okay. So again, by that theorem, that existence of a unique solution theorem I read off to you, if the point from the condition were up here, then I set my region to be the top half plane, and a solution, a unique solution to that differential equation, that initial value problem, would be guaranteed. If the point that I'm looking at, if the point from the condition were down here somewhere, then this region below y equals 0, the lower half plane, would be a valid region to ensure that a unique solution exists in that region that passes through that point. Okay. All right, so that's just one example. That was a pretty simple one, right? Because that f function, f of xy, only depended on y. All right, so here's another example. So this time I have x times y prime, or x times dy dx equals y. And again, there's some initial condition involved, some point x0, y0 involved that the solution has to pass through. All right, now this is not like the previous one. Right? The previous one was set up the way we wanted. All right, I want these when I'm talking about using this theorem. Right, when you talk about using this theorem, the equation has to look like this, where the y prime is alone, dy dx is alone, solved for, and then the other side is the f of xy. So if I want to, this equation right now doesn't look like that. So I would need to divide by x on both sides to get it to look like that. So dividing by x, we have dy dx would be equal to, y divided by x. Okay, and now it looks like this, and then some initial condition again. Right? And here, the f of xy, that function of x and y in question now, is this y divided by x. All right. And then again, the same question occurs: on what regions are both this and its partial derivative with respect to y continuous? All right. Okay, so let's look. F of xy is y divided by x, so clearly x can't be 0, right? If x were equal to 0, which I'll draw up, this would not be defined and therefore not continuous, and it's a rational function. It's continuous everywhere else, except that on the line x equals 0. And then the partial of f with respect to y, again, you treat y like the variable and x like a constant. Well, this would just be 1 over x then. So again, same thing. Either way, the function f here, the partial of f with respect to y, not defined at 0, not continuous at 0. So when we're talking xy plane, x equals 0 is no good this time. So here's x equals 0. Right? That's the y-axis. So wherever this point is, right, wherever this point that's mentioned by the initial condition, wherever that is, as long as the rectangular region you can use that guarantees a unique solution by this theorem, as long as that rectangular region doesn't include any piece of this vertical line x equals 0, you're fine. So let's say again, say the point was over here. Right? Say this was x0, y0 from the initial condition. Well, then the region I would use, the largest possible, would be the right half of the plane. Right? So I could use the right half of the plane as this region being talked about. So basically any place where x is greater than 0. Or, that's only if the point from the initial condition is over here. But if the point from the initial condition is over here, well, then I would use the left half of the plane, right, where x is less than 0. And by this theorem, there'd be, and this theorem would guarantee that this initial value problem would have a unique solution over here that passes through that point. Again, you could pick smaller regions if you wanted, but we're trying to make them as large as possible. Like again, say if the point was over here, this region would be fine. This rectangular region would be valid, and a unique solution would exist to the initial value problem that passes through this point in this region. But again, we're trying to make it as large as possible, and so that it's not including x equals 0. Okay. All right, and then I have one last example that might be a little trickier. Because so far, the partial derivatives have been pretty simple. I'm not trying to go too crazy. The last example, though, is a little more involved. But the same questions, same instructions. Determine a region of the xy plane for which the given differential equation would have a unique solution whose graph passes through a point in that region. Okay, so here I have 4 minus y squared times y prime, or dy dx, equals x squared. And like I said before, this is not, in order to use that theorem, right, in order to apply the theorem, I need to get the equation to look like this, where y prime is alone. Okay, so first I'll divide by the 4 minus y squared. So we have y prime equals x squared divided by, and then 4 minus y squared. Right. And now I have it in that form. This x squared divided by 4 minus y squared, that's going to be my f of xy. Right. And then we'll take the partial with respect to y. Right. So f of xy equals x squared divided by 4 minus y squared. And hopefully you can tell that y cannot be 2, y can't be negative 2. Right? Because if y were 2 or negative 2, you'd be dividing by 0 here. And again, this being a rational function, it's continuous everywhere except for where it's undefined. So it's continuous everywhere except at the line y equals 2 and the line y equals negative 2. Okay, now the partial of f with respect to y. I think it would be easier to look at f this way as x squared times 4 minus y squared to the negative first, right, just to make it easier to take the partial. Remember, you're treating x like a constant. Right? Y is the variable, and you're treating x like a constant. So this would be the constant times, and you have negative x squared times 4 minus y squared to the negative second times, and then chain rule, the derivative of 4 minus y squared would be negative 2y. And then putting this all together, and if I don't like having negative powers too often. The numerator would be positive 2x squared y. Right, negative x squared times negative 2y, and then divided by the quantity 4 minus y squared squared. Right, so there's the partial with respect to y, and it would be undefined in the same place. Right, so these are the restrictions here. Y can't be 2, y can't be negative 2. All right, so let me draw the xy plane with those restrictions put in. And then we'll have some possible regions where unique solutions to the initial value problem would exist. So again, here's the xy plane, and then I'll mark off y equals 2. So say there's 2 there. Right, so there's a dotted line. I can't have that in my region, any part of that line. Same thing for -2. Right, can't have any part of this region in the line either. So really there are 3 largest possibilities. All right, if the point from the initial value problem was up here, all right, if the point were up here, then I'd use the part of the plane where y is greater than 2. All right. So one possibility, the region is the part where y is greater than 2. All right, and again, that's a plane, part of a plane, right? Another possibility, what if the point were in here, in between this band? Well, then the region would have to be this region here between. All right, so between -2 and 2. Again, that plane. If the point were in there, then there'd be, again, this theorem would guarantee that there'd be a unique solution running through the point. And the third one is if the point from the initial condition were below y equals -2, your region would be this plane here, the plane where y values are less than -2. And by the theorem, you'd be guaranteed a unique solution to the differential equation and a unique solution to the initial value problem that passed through any point down here. All right, and that's about all. Three possibilities are, again, you could pick something smaller, right? If this point were the point mentioned in the condition, I could have this rectangular region, but again, we're trying to make things as large as possible. Yeah, all right, so again, that's it. All right, that's it. This is, again, for only first order initial value problems. In order to determine, which regions would have a unique solution that's guaranteed by this theorem, you got to solve for y prime and figure out where that function and its partial derivative with respect to y, where are both of those continuous, and you'll have determined regions for which this theorem guarantees the existence of a unique solution passing through any point in that region. So hopefully these few examples help you out when you're working on problems similar to this, and thank you very much for watching.